Hi everyone, welcome to this video, and this is part one of a two-part videos for three-phase transformer systems. And this one particularly will be diving into the calculation of the active and reactive and apparent power, as well as line voltage and currents. So this question has several subparts that I'm going over each one of them in each slide. So the first one is asking, what is the total apparent power supplied to the residential area? I would first like to draw a roughly how it looks like in general in terms of Y delta configuration that the question is asking. Okay, imagine that roughly this looks like the scenario that we are expecting. So I'm connecting the wiring, and also it says that the primary side has a 330 kilovolt, which is going to be converted down to 11 kilovolts. And demanding power is going to be 18 megawatts. So that's the power factor is going to be 0.92 as well. So this is all the information that we're given. Now, in terms of the total apparent power supplied to the residential area, we need to consider the fact that when we're talking about the power, it is essentially S times cos theta, which in this case, cos theta is the power factor. So whatever is given to us as 18 megawatts is essentially a multiplication of S times the power factor. In this case, the power factor is going to be 0.92, as the question itself suggests. Now, S as the apparent power can be easily calculated as follows. 18 megawatts divided by 0.92, which is going to be roughly around 19.5 megawatts, mega volt amperes indeed. So let's dive into the part B of the question. Part B is asking the apparent power supplied by the high voltage line. So in this case, the high voltage line is the left part of the circuit, which is supporting 330 kilovolts. And essentially, we need to be mindful of the fact that the whole transformer is going to transform the voltage and the currents, but it essentially preserves the amount of the power that is going to be delivered to the load. So essentially, if we have the information of the power from the secondary, that will be given, that will be exactly the same as the apparent power delivered to the primary as well. So the apparent power of the secondary of is going to be the same as apparent power of primary. That may not be true actually for the active or reactive powers, but essentially for the total power or the apparent power, that is true. So in terms of the apparent power of the primary, we found out that the S turns out to be around 19.5 megavolt amperes. So that is going to be the same for both primary and secondary. So let's dive into this third question. The third one is asking part C, the current in the high voltage lines. So we need to consider that in terms of the voltages and the currents in the primary or secondary, we know that S equals square root of 3 times V line times I line. So we need to consider the line voltages and line currents multiplied by each other. And also there is a square root of 3 factor that needs to be multiplied to get to the to the apparent power. Now that we have the apparent power of the high voltage line, which is the primary side, as well as the voltage, which is also given here, we can then easily find the IL. Now let's try to simplify this. This would be S square over square root of 3 VL, and S turned out to be around 19.5 megavolt ampere, and square root of 3, V is going to be 330 kilovolts. So if you simplify that, you get to the current value, which is going to be around 34.2 amperes. So that is the current line, which is passing through the primary, 4.2 amperes. Fourth question, however, is asking the current in the low voltage lines. So for the low voltage lines, we will adopt the same methodology. We know that S equals square root of 3 VL IL, and in this case, IL, or the line current, is going to be S divided by square root of 3 VL, and S turned out to be 19.5 megavolt ampere divided by square root of 3. VL in this case is going to be 11 kilovolts. That's the line voltage, 11 kilovolts. So if you simplify this, you would get to I line of around 1026 amperes. Part E of the question, by the way, is asking the current in the primary and secondary windings of each transformer now. So we're no longer looking for the total line currents, but now we're looking at the each windings of the transformers. We need to now know the fact that in the primary and the secondary, we have two different types of transformers. In the first one, we have the Dwight configuration, which in this case, I line is exactly the same as I phase. Essentially, the question is asking about the phase currents from the line currents. So in the primary sector, phase currents are going to be the same as the line currents because they are directly connected. So for primary side, I line equals I phase, and that equals what we just found to be around 34.2 amperes. However, for the secondary, we have the delta configuration, which in this case, the line currents are no longer equal to the phase currents, but there is a factor of square root of 3 between them. So essentially, I line for the secondary, I'm just writing it in this case, is square root of 3 times of I phase of the secondary. And in this case, I phase, or the winding current of the secondary, is going to be I line of secondary divided by square root of 3, which is going to be around, I line of the secondary was about 1026 divided by square root of 3, which is going to take us to around 593 amperes, roughly. So these are the currents in each phase, or in other words, each winding of these transformers. And finally, the last part of this question is asking the load carried by each transformer. So we know that we have an apparent power on each side that is equal. However, the load per transformer is going to be the load per transformer is going to be the total apparent power divided by the number of the transformers. Number of transformers. And in this case, since we're dealing with 3 single-phase transformers, we're going to actually divide that by a factor of 3. So essentially 19.5 megavolt volt amperes divided by 3, it's going to be around 6.5 megavolt. So essentially, this is going to be 6.5 megavolt amperes of the load carried by each transformer. So now let's take a look at the second question. The second one is saying 5 single-phase step-down transformers, each rated at 60 megavolt amperes, 132 kilovolts down to 33 kilovolts, are connected in a delta Y configuration on a 132 kilovolt grid, which is exactly the same as the rated one, to distribute electricity to a suburban area. This setup is designed to support a combined load of 150 megavolt amperes at peak times. Find the currents in the transformer's primary and secondary windings. So I would again try to roughly sketch the scenario for the delta Y configuration, that how it looks like. And I'm interested to just draw the lines. Okay, so imagine that this is the configuration given in the question. I'm just gonna write down all the necessary informations here. So 132 kilovolts over here, 33 kilovolts here, and the total load is going to be 150 megavolt amperes. Now the question, well, is saying try to find the currents in each transformers. Now that actually we're not given any information about the power factor, we can easily consider that to be 1. Having said that, we know that again, with respect to the apparent power and the total power, we have the following expression such that S equals, in this case, P, which is square root of 3 I line V line. And in this case, we know that 100 megavolt amperes is going to be delivered to the load, and we have this amount of voltage. So we have the line voltage in the secondary, we have the power, so we can easily find the current in the secondary. This is going to be IL of secondary going to be P of secondary divided by square root of 3 VL of secondary. Having said that, we need to also be mindful of the fact that the power that we're talking about in both cases are going to be given for the whole case. However, we have 5 individual transformers. And if you want to find out the current per transformer, we need to divide this whole current by a factor of extra factor 5. So I'm going to actually write down here a factor of 5 to elaborate on the fact that this goes back to each transformer. So if we consider the power in the 150 megavolt amperes divided by 5, square root of 3, and the voltage is going to be 33 kilo. So essentially, that would take us to around 524 amps. Now we need to consider the fact that when we're talking about the secondary line currents, since this is a Y configuration, the phase current is going to be exactly the same as the line current. So for the secondary, the phase current is going to be the same as line current, and that is 524 amps. Now, moving towards the primary side, we're going to actually employ the same line of thought in order to calculate the current of the line. So I line of the primary is going to be the primary power divided by, again, factor of 5, square root of 3, VL of the primary. And in this case, we again are going to use 150 megavolt amperes divided by 5, square root of 3. But this time, we're going to employ this voltage because the primary voltage is now 132 kilovolts. And if you simplify that, you would get to a number of 131 roughly amps. So that's the line current. However, the phase current for the first one is different from the line current with a factor of square root of 3, such that this equals square root of 3 times I phase of the primary side. In that case, I phase of the primary side is going to be 131 divided by a square root of 3, which is going to be around 75.6 amps, roughly. So that is how we would be able to find the currents in the primary and secondary in terms of both delta and Y configuration. So let's dive into the third question. The third one is asking: a textile factory operates a series of lighting circuits requiring a total of 18 kilowatts lighting circuits. So let's dive into the third question. A textile factory operates a series of lighting circuits requiring a total of 18 kilowatts of power. This lighting is powered through a three-phase Y-connected transformer that steps down a voltage from 480 down to 208 60 Hz. Assume the transformer operates at an efficiency of 92% and the overall power factor of the lighting circuit is 0.9. Calculate the current drawn from the 480 volt supply by the transformer when the lighting is fully operational. So this goes back to the factor of how the power is going to be stepped down in terms of the efficiency as well as the power factor that we have over here. So essentially, we typically know that P is S times cos theta. However, that is not the most complete equation because it doesn't consider the efficiency. It only considers the power factor. So we need to actually multiply that by another factor of eta that allows us to find the power in the real format. So essentially, this is the efficiency. Here is the power factor, and here's the parent power. In our question, by the way, we are given the information about the power, the actual power, real power in terms of kilowatts to be 18, which means that this whole multiplication turns out to be 18 kilowatts. Now, in terms of S, we know that S is a factor of square root of 3 VLIL. Then we have cos theta as the power factor. The power factor is going to be 0.9. So 0.9 times the efficiency, which is going to be 92%. So we're going to actually plug it in here, 0.92. And also we need to know that this whole thing is going to be driven by a voltage of 480. So I'm going to simplify that with 480 volts. So using this equation, now we can solve for IL because that's the current that the question is asking for. So let me just simplify this a little bit. IL equals 18 kilowatts divided by square root of 3 times 480 times 0.9 times 0.92. So if you simplify this, you get to a number of around 26 amps. So that is the current driven by this transformer to provide that much of power. So here is the exercise that I have designed that is equally important with respect to the previous questions, as well as solvable with respect to the concepts that we just went over in this tutorial. Feel free to ask your questions in the comments and like this video if you like it, and subscribe for more videos in the upcoming days. You have a good one.